Okay, so what I'm going to be going over in this demonstration here is how to use an oscilloscope for transient capture. So the way I'm going to do that is I'm first going to show how you normally do a transient capture in a simulator, and then after that I'm going to do the transient capture on the simulator oscilloscope here. And then after that, I'm going to do the transient capture on a real-world oscilloscope. So that's the general outline for what I'm going to demonstrate here. So first I have this this very simple first-order RC transient circuit. And so I have this resistor here as a discharge path resistor. And so when I close this switch here, when this switch is closed, then this capacitor is going to be charged up. When I open up the switch, this capacitor is going to discharge through R2 because that's all that's going to be left and provided as a path for it to be able to discharge through. So first of all, we need to know what type of a time span to graph this over. And so what I'm going to be looking at here is the RC transient or the RC time constant. I'm going to look at the RC time constant and multiply that time constant by 5 in order to get an idea of what type of time span should I be graphing this over. And you have to do that so that you know what to expect. So for this circuit here, when I close the switch, I'm going to have both R1 and R2 included in the circuit. So how do I come up with a figure of the net resistance? Well, if you just reorder this circuit just a little bit, just to see the net effect on C1, what you see is that, well, of course, you have this voltage divider here, so that all C1 is going to be subjected to when this is in its voltage divider configuration here is the open circuit voltage, and that open circuit voltage is the voltage divider amount coming out of this node here, coming from this node here, right? So that equivalent voltage for VOC is going to simply just be half of 5 volts because R1 and R2 are equivalent. So VOC is going to be 2.5 volts. That's all it's going to be imposed for voltage across C1. So we know at least that's how when it gets charged up, that's what we expect our vertical amount of amplitude to become. Okay, it's not going to go over 2.5 volts. Next is, well, for the RC time constant itself, what is the net resistance of all of this going back here during the charge up? Well, that's basically the net equivalent resistance, and you find that out by making your voltage source here a short. And so when this is shorted and you only have R1 and R2 left, that is just R1 parallel to R2 for what C1 is going to be subjected to for an equivalent resistance. So R1 parallel to R2 is just going to be half of this amount because of your 1K, because R1 and R2 are both the same value, and it's going to be half of that value when you calculate them being parallel to each other. And so you're going to get 500 ohms. So during your charge up, you're going to have 500 ohms times 10 microfarads, and you're going to multiply that by 5, because by 5 time constants worth of time, Any transients have basically come to their settling point, and you're basically all your transients are gone in the circuit, and it's going to be settled by then. So that gives us 25 milliseconds to take a look at this on its way up when it's closed. Now, how about when I open up the switch, and how's the discharge going to look? Well, the only thing that's going to be included in the circuit under those conditions is C1 and R2 for a complete path. These are still here, but it's just that there's no path for C1 to discharge through. It cannot discharge through R1 because the switch is now open. So with that being the case, that RC time constant is simply just going to be double the original amount. Why? Because these are both the same resistance value, and when you take one out and they are no longer parallel, you're only left with this R2, and so that amount of R2 is 1 kilo ohm times 10 microfarads times 5. So it is exactly double, 50 milliseconds. So if you want to not have to switch your time base to match each scenario, you're best off with choosing the larger of the two. That way you're going to be able to see both on the same time scale, on the same time span. And so I'm going to choose 50 milliseconds for that. So that's what we can expect to see, 50 milliseconds worth of a time span, and we're going to expect to see 2.5 volts when it's charged all the way up across C1, and then when it discharges, of course, it's going to come back down to 0. So I'm going to go ahead and put that capacitor where it was originally located, and I'm going to do this with regular transient analysis. And by the way, just don't forget to make sure you have your switch closed. So regular transient analysis, and I'm going to run it for 50 milliseconds, and my output is going to be at this node here, V of out, which is that node there. And then I'm just going to go ahead and run it, and this is what it looks like. Switch is closed, and it's charging up, and on its way of charging up, I'm graphing it with 50 milliseconds, but remember that charge should be virtually complete by only 25 milliseconds, which is what this is looking like. So I'm going to go ahead and make this larger so I can see more detail. Let me see, how many data points do I have? Plenty. Okay, so take the cursor and just tell the cursor to go to 250 milliseconds, 25 milliseconds. That's cursor 2. I wanted cursor 1. Try that again. 25 milliseconds. Okay, so by then we're at like 2.48 volts there, and that's basically, you're pretty much done. Okay, that's your 2.5 and your 5 time constants. So that turns out good. That's what we'd expect. Now for the discharge, so I'm gonna open the switch, and as far as the discharge is concerned, I'm gonna put in here 2.5 volts for initial condition because that's where it was. And with that initial condition, I'm going to make sure that this is user defined, and I'm going to go ahead and do the same type of a graph again. Let's see what we get. So this is what we get here. So as you can see, it's still not settled yet. The cursor is still at 25 milliseconds, and it's still not settled yet because you have 200 millivolts there, and or 205 millivolts there. But how about if you tell this to go all the way to the end, which is what, your 50 milliseconds. And what do we have here? Now we have 16 millivolts. So that's, you know, really getting really small there. So that's basically it. That's your 5 time constants, and that's how it generally works in transient analysis when you use it in its normal way on this simulator. Okay, so now what I'm going to do is do the same exact thing, but I'm going to use my oscilloscope in my simulator in order to capture a transient snapshot. So in order to do that, of course, you're going to need to set up your oscilloscope the right way, and you're going to have to use interactive type of simulation in this program. Okay, so I'm expecting to see 2.5 volts, and you know, at the top, and I have this scaled for 1 volt per division, so I got 1, 2, 3 volts maximum, so that makes sense to use that. And then my longer of the two transients is 50 milliseconds for a time span. So as long as I have enough to show 50 milliseconds here, that'll be appropriate. And I have this time base set at 5, so I have how many divisions? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 times 5 is 50, so that should be perfect for this circuit setup. So now the next thing you want to do is make sure, after your time base and your vertical scaling is set up correctly, is you want to make sure that your trigger is set up correctly. So at first, what I'm going to do is I'm going to charge the capacitor up, and I want to make sure that I take this initial condition away. Just don't even specify it anymore. Take that initial condition away because this is going to like simulate more of kind of like a real world sort of an action to it. So I took that away, and make sure that the level that you trigger at is going to be a little bit more than 0 volts. I'm going to put it in millivolts, and I'm going to use maybe like something suitably sort of small, like maybe 1 millivolt. I wouldn't go any lower than that. Maybe make it 5 millivolts, so that when it rises above 5 millivolts, then that'll trigger the oscilloscope to take a snapshot of what's going on until the end of the screen. And so in order to do that, I'm going to put it into single mode instead of auto. And again, I'm going to capture this when the edge of this rises. So it's on a rising edge trigger, and that's going to be on channel A. So that's basically it. And this is going to be DC coupled, and it's going to be in a mode of Y versus T, which is the horizontal axis, you know, your voltage versus time. Okay, so with that being the case, I'm going to take a snapshot for the charge up amount, and actually the charge up amount is only, we're going to expect to see what, 25 milliseconds. The discharge is 50 milliseconds, but we'll keep it the same for both. So I'm expecting 25 milliseconds for my charge up. And last but not least, you have to make sure that you tell this to use interactive simulation. And the output is irrelevant because it's what is connected to the oscilloscope there. So I'm going to go ahead and run that, and let's see what we get. So at first, it's not going to do anything automatically. It's going to wait until I close that switch. So let me close the switch, and then I've captured it. I got it. So now I can just stop my simulation, just to let my computer take a rest, and then take a look at this data. So, as we thought, halfway up through this, and we said, you know, for the charge up, you're going to have both resistors included. So that's your 25 millisecond time constant, your charge up time span, which is your 5 time constants for that particular circuit configuration. And so let's go to 25 milliseconds here. I think with this you can click it and nudge it a little bit, but I don't know if you can actually enter a cursor point. Okay, that's exactly 25 milliseconds. And what do we have? 2.483 volts. Okay, 2.483 out of 2.5 means you're done. So that makes perfect theoretical sense. Okay, so next thing now, we're going to leave the oscilloscope set up in just the same way, with the exception that now we are going to trigger it when it's going down. We're going to have it on a negative edge trigger, and instead of being 5 millivolts, well, we're all the way up there. Right now we're at what is it, 2.48 volts. So we're going to say that we're going to trigger it when it gets below 2.48, because we're at 2.483. So we know we have at least that much. We're going to trigger this when it's at like 2.480. Okay, so I'm going to put that in here. We can switch from millivolts to volts if you want, or you can just keep it in millivolts. That'll be 2,480 millivolts. That'll give you your 2.48 volts. I'll just leave it in millivolts. A negative edge trigger, and it's going to be put into still keep it in single mode, and everything else will be kept the same. And I'm going to actually make this oscilloscope screen smaller so that we can see the action of the switch when it switches. And so I'm going to go ahead and start it. And so it's going, and so now I'm going to open the switch and see if it captures it. And so it does. Okay, so now I'm going to stop my simulation and then just take a look at the data. Okay, so this is the transient that takes longer, and so if I go all the way over to the right side of it, as far as the cursor can go, it's showing me that at time 50 milliseconds I have, for channel A, I don't have channel B hooked up, but for channel A I have 16.7 millivolts. So basically it's done, and that's basically it. So that all worked out as expected, and so that's our discharge curve. That's what it's going to look like. So next, what I'm going to do is I'm going to take a look at doing this on the oscilloscope, real world oscilloscope, and use the same type of utilities on that oscilloscope as well, because generally all oscilloscopes have these basic functions in order to capture transients, and a real world oscilloscope is automatically going to be interactive. It's not like it's in a simulator that, you know, you have to set up transient if you're using transient instead of an interactive real world type of a simulation. Okay, so let's go ahead and take a look at that next. This is my breadboard build setup here. I have my 2 resistors, my capacitor, and I have my 5 volts there. I have all of that set up, and so the next thing is to take a look at the oscilloscope settings. And first you want to make sure that your time divisions, which is your horizontal knob, that your time span is set correctly. I have 5 milliseconds per division, just as I did in the simulator. And as far as my vertical is concerned, I have 1 volt per division, and I have 1, 2, 3, 4 divisions, so I'll be able to see a full 2.5 volts there. It won't look too small, but it won't, you know, be off of the screen either. So those are appropriate levels for that. Next, I need to make sure that my trigger is set up correctly. And so the circuit is discharged right now, so when I flip this switch, it's going to charge up. So initially what I'm going to do is I'm going to take a look at the charge up first, and then I'll do a discharge. So remember, with the charge up, we're looking for a total of 25 milliseconds for charge up. And so what that means here is, you know, 25, I got 1, 2, 3, 4, 5, 6 divisions here. So you know, I only need 5 times 5. That'll give me my 25. So 1, 2, 3, 4, 5. I'm looking for it to basically rise and then be all the way past its transient state when it gets to about right there. But that depends on where you set your horizontal position. I'll leave it where it is currently at now, but you'll see that you can offset that and you can put it at a different spot, and I'll demonstrate and show both. So on this oscilloscope, just press the button and then it'll put you back to your default value of 0 for that. Okay, so that's my time span set up there. So now, okay, let's go on to the trigger. So in my trigger menu here, I'm going to use edge, and I want my source to be channel 1. I'm not going to use channel 2 for anything. And my slope, I'm going to be looking for a positive slope, because remember, it's going to be charging up. And also, well, right now it's in auto, but I'm going to set that up for single. And also remember that I want to make sure that my trigger, see the trigger level there? By turning this knob, I can adjust the trigger level. I want to trigger it probably at about 80 millivolts. That seems to be about good as far as I see it. If it doesn't work, you can always try a higher setting, but you don't want it to be too high, because you want to capture it as soon as it starts to change, but you don't want to set it too low either. It may not trigger it, or maybe it might be triggered simply by noise. So just set it to a normal, you know, amount, but you know, don't overdo it in either way. All right, so with that being the case, it's on single. That's the run mode. It's on single, and I'm going to flip this switch and let's see if it captures it. And it did. It captured it. That looks a little unexpected there, that heavy step. So what I'm going to do is flip the switch back down. I want to get another capture of that. I'm going to need 80 millivolts and up. Let's try it again. It triggered it. Okay, so that's just what I have here for this circuit. Okay, so you can make this disappear by doing that, and then you can use your horizontal position to take it and put it, you know, wherever you need to put it. So again, for this particular curve, we said what, 25 milliseconds, right? So 5 of these divisions, that's 3, 4, and 5. So that's consistent. That looks pretty much like it's done, and that's all there is to that. Of course, you can turn on cursors and you can start to measure things. So I'm going to take my cursors, make them as time cursors, leave it on manual, switch to cursor A, and go over here. Then go to cursor B, try to locate that. So over here it's just hidden initially. And so I'm going to be expecting for that to be, so by the time it gets there, we're saying that that's done. Okay, so if I go ahead and I hit the run stop and take off the single, then my trigger now automatically goes back to automatic, and so it's just acquiring data. Okay, so I want to turn my cursors off just for right now. Let's get rid of this menu, and that's what we have. So now we're at our 2.5 volts, right? We can actually take a look at the measure. See your VRMS, approximately 2.5 there. Because of the noise being superimposed on top of it, you know, it's as high as 2.8, but those are peaks. The RMS is the better value to be looking at for this, which is the 2.5. So we're at 2.5, and now we're going to go to our trigger menu, and this time we want to put the slope on negative. So it's going to be declining, it's on negative, and you know, when it discharges, and the type is going to be edge, we're going to leave everything set the same way. So I'm going to be all the way up here, and what I want to do is I want to trigger it as soon as it gets just a little bit below that, and that'll make good sense. And that trigger level is approximately at like 2.4 volts, so that way I'll be, you know, more guaranteed to capture it when I do this. So I'm gonna put the run mode into single, and basically that's like snapshot mode, and then I'm gonna operate my switch, and there I have it. So it captured that, and that's what I have there. So remember, with the discharge mode of operation of this circuit, where we estimated, or we calculated actually, that it's supposed to be 50 milliseconds. Okay, so let's take a look at this. It's about right there. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So right there, it should be done. And even without using the cursors, let's just take a look. Yep, because you have 11, 12 there. Yep, by then it's done. Okay, so let us just bring that over a little bit more. Turn our cursors back on. This is why it's good to do this with the correct time base. Even though this is correct, it's just, you know, on the edge of what this can do. You're only left with 2 more time divisions, but let's see. Let's go all the way back to approximately there, and then that's cursor A, and let's take cursor B and move it to 50 for a delta. I'm looking up here at a delta, 50 milliseconds. So that should be it, and that's what we have, because we're just a little bit over here. We're a little bit to the right on cursor A, and we're also a little bit right on cursor B, so that compensates correctly, and so that's what we have. That is just what we have there, okay? So both of those checked out just fine, and then that's what it is. That's what you can use. You can use this for, okay? So even after you've captured it, if you want less detail, you can also do this on this scope. Apparently, you can just simply go further out. It's going to operate kind of like a zoom button, or you can leave it like how you had it. I think it has a window zone that you can define with this, and then you can tell it where you want it to be, and then you can hit zoom to zoom in or go back to how it used to be. But I can also take my horizontal, make that smaller, just so I can get my cursors onto the screen and see them. Reposition this. Then take my cursor A, that's the start of it. Take cursor B and look for 50 milliseconds there, and that's what we have. It's settled by 50 milliseconds, so that works too, just to check this transient response out. So that's how you can do transient response on an oscilloscope. So hopefully that was helpful. Thank you for watching. Have a nice day.